If you want to do well in grade 11 and 12 Newton's laws, this is a video that you do not want to miss. In this video, we go over how to draw different types of free body diagrams for different scenarios. Grade 11s and grade 12s, you have to know how to draw a free body diagram in order to succeed in your physics exam and in order to do well in this section, so let's go. You need to know how to draw force versus free body diagrams in your exams in grade 11 and grade 12. And let me tell you why they are so important in order to succeed in your grade 11 and grade 12 exams. First of all, they are easy marks. So in your grade 11 and your grade 12 exams, you will be asked to draw a few free body diagrams. And these diagrams can be 5 marks in total, some of them. Those are free marks if you know what you're doing. They're your easy marks. You don't even really need to study for them. You need to get these correct in your exam, so you can't afford to lose marks on these. And the second reason why they are so important is because drawing your free body diagram correctly can help you set up your equations for Newton's laws, for Newton's first law, for Newton's second law. When you see the forces on the free body diagram and you know in which direction you are working, so is the object moving along the horizontal or the x direction like this, or parallel direction, or is it moving along the y or the vertical or the perpendicular direction? When you see your free body diagram, you see the forces and the way that they're acting. Knowing that can make such a difference when drawing your equations or writing out your equations and answering Newton's laws questions. So I hope you're not skipping this video. You need to know this stuff in order to succeed in Newton's laws. Now, first of all, very briefly, force versus free body diagrams. Both can be used to represent the forces acting on an object. We often use and ask free body diagrams in your exams. So I am a teacher. I've been working for many years now. I mark up to matric level. I set papers up to a matric level. I moderate papers up to a matric level. We prefer free body diagrams. Okay. And so do your external examiners at the end of the year. And both of them use arrows. Remember, vectors can be represented by arrows. Forces are vectors. They can be represented by arrows. The length of the arrows represent the relative magnitudes, and the arrowheads point in the direction of the force. That's exactly what that says behind me. So here you can see different examples, and these are actually what we call force diagrams. Now you can immediately recognize a free body diagram. Free body diagrams are when the object is represented as a dot. Okay, so we use a dot and all the forces or all the arrows point away from the dot. So this situation that's happening right over here, that will never happen in a free body diagram. You never have arrows pointing towards the dot. They point away from the dot. So in these force diagrams, we can almost see where the forces originate from as well, which is different to a free body diagram. So in a force diagram, we represent the object as the object itself, like a box or something. So these are obviously boxes being pushed or pulled or pulled or whatever. And you can see here, from the center of the object, that's where they draw the weight vector. The normal force vector is drawn from the surface of the table, and that's because it is a force that the table exerts on the object itself. So these are force diagrams. I'm going to show you how to transform them into free body diagrams, because as I mentioned, those are a lot more common. So starting with the one on the top left over here, this is very easy. You draw your dots. FG acts straight down. You can call it FG, you can call it W, and FN acts straight up. Please remember arrowheads. Please remember to label it. I was telling one of my classes the other day about a learner who in my first or second year of teaching forgot to put the arrowheads on all his vectors throughout his entire test. He lost a lot of marks doing that. So don't waste marks or lose marks on silly things. Then the one top right, we've got, here's my free body diagram. We've got FG acting straight down. That's FG, the force of gravity or weight. We've got FN acting straight up. Okay, the force that the table exerts on the object. And we've got F applied acting upwards and at an angle. So obviously you have to draw this acting at an angle. That is FA or F applied. Now, if this was a free body diagram that we were doing for marks, you would get 3 marks because you are giving me 3 arrows. So this would be worth 3 marks. This would be worth 2 marks. And very important, teacher tip, always look at the mark allocations on your free body diagram. So if the free body diagram says 5 marks, you know that you need 5 arrows, 5 forces. If the free body diagram question says 4 marks, you need 4 arrows, 4 forces. Very simple if you think about it like that. What that also means is if you draw in any extra forces by accident, they're minus marks. Okay, we take marks away. And included with extra forces is also when you break up the forces into its components on the free body diagram for marks. So what I mean by that is we have learned in other videos that because the applied force here is acting at an angle relative to the surface, we know that we can break it up into its horizontal force, which is FAX or FA parallel, and its vertical force, which is FAY. Although that is true, and that is true, we can break that force down into its components. On your free body diagram for marks, you never draw those components. Don't draw them in. Those are considered as extra arrows. They will deduct marks. Draw the forces as is, please. Now, with that also being said, I often tell my learners that if they ask for a free body diagram for marks, do it properly. Do not include these little extra green arrows that I just drew in here. However, when you are doing your calculations, I always draw a rough free body diagram. And on that free body diagram, I do resolve my forces into components. And the reason I do that is because it's helpful when you do questions. I'll show you that in the next video. Let's do the last free body diagram. So we've got box. Now, take note, this box is not resting on a table. They're not saying that it's on a surface. We are obviously going to assume that this is a box. It has a mass, so therefore it has weight. Weight acts straight down, Fg. This force is an upward force of 2 Newton. Whether or not that is a normal force, I don't know. Okay? It's just the 2 Newton force. Then we've got 3 Newton acting to the left. So that arrow must point that way to the left. And this is 5 Newton to the right, so that must go to the right. In my opinion, these are all probably applied forces that they're acting on some random body that's floating, but whatever. I'm now going to show you how to draw these free body diagrams. I know the first one's easy. We've got our object as a dot, always object as a dot, and you'll see that I draw my dots quite big. I will show you why I'm doing that now. We've got FG acting straight down. Please use a ruler as well. I am writing on something that I can't use a ruler on, so my lines are not going to be perfect, but you will use a ruler. We've got F applied going to the right. Please call it F applied. Please don't say F up or something like that. And then we've got friction, assuming that there's friction going to the left. Always assume that there's friction unless they state otherwise. Okay, that's a nice easy one. Try and make the arrows the correct length. So because this box is not moving in this direction, the vertical or the up-down direction, make Fn as equal to Fg as you possibly can. And I just told you I don't have a ruler, so I'm not measuring mine out, but try and make it equal. Please don't do this. That's Fn and that's Fg, because that's not a true representation of what's going on here. This box is not moving in the y direction. It's not moving perpendicularly or in the up-down direction. So these arrows must actually be the same length. Okay, this is a very similar diagram to the one we did over here, so I'm not going to do that one. But I want to focus on doing one where we have an object on a slope. Now, this often trips students up. They mess this up, their forces are going in the wrong direction. So I'm going to show you my teacher tip on my best way that I do these free body diagrams. And that is, in the beginning, when you're not sure how to do these, I want you to draw the slope in pencil when you do your free body diagram, then you're going to erase it. Okay, I'll show you what that means now. But before we do the free body diagram, I just want to remind you, remember the normal force acts 90 degrees relative to the slope. Okay? The weight acts straight down and friction will go that way. Just keep that in mind. When I draw the free body diagram, this is how I recommend you do it. Okay, so I recommend you take a pencil, and just like we have the slope over here, I recommend you take a pencil and you draw the slope in pencil. Now, I don't even know if you can see that. That looks very, very light, but I've drawn the slope in pencil. Maybe I should make it a bit darker just so you can see what I'm doing. Okay, slope is in. in pencil. Now remember, the object is represented as a dot. Draw a nice dot for me. FG, or the weight, acts straight down to the ground. So this is the ground here. That's why I draw the slope in, so you can see the ground. This is FG, or weight, W. The normal force acts 90 degrees relative to the surface. So you cannot draw the normal force in going straight up like that. Okay? You cannot draw the normal force in like this, because the object is not on a flat surface. If the object was on a flat surface, normal force would go up like that, but it's not. So that is wrong. You have to look at the surface, and this is why I draw it in pencil. I look at my surface, and do you see that my surface is going like this? I know the normal force doesn't go like this. It has to go at 90 degrees relative to the surface. So that angle between my hand over here, which is the slope, and my pen over here, that must be 90 degrees. And that's why drawing in the surface or the slope may make it easier for you. So that is what we're looking for, 90-degree angle. I'm not expecting you, or we're not expecting you to use your protractor, but try and make it look 90. That's Fn. Now look at F applied. It is parallel to the slope. You know what parallel means? It's parallel to the slope. So here's the slope. So F applied must go along that slope over there. F applied. And as you know, friction is in the opposite direction of motion. So let's pretend the box is going up the slope. But it's also parallel to the slope. So there's my slope. It must be along that slope. There's Fk. Once I've got my forces in, just make sure you draw your arrowheads nicely, you label it. Then I'm going to erase my slope. Like that. There we go. There's your free body diagram. Now remember, on the diagram that you do for me for marks, you leave it as these forces. You do not add in any extra arrows. You do not resolve weight into components. But when you are now doing a Newton's law calculation, say you're doing Newton's second law, F net equals ma, and you need to list all your forces here for me. Okay, you need to list all your parallel forces. Then I do need to know the components of Fg. So then I redraw this diagram. Remember, it's not the one for marks. I've drawn it for rough now. So on the side of my page, I scribble it in quickly again. I draw it in rough, and I add in my components. So there's F applied perpendicular, and here's F applied parallel. Now with those components in there, I can see the parallel forces. I can see the perpendicular forces. So doing that is very, very helpful. So what I do now is I say, okay, cool. I want to work out the net force, or I want to work out, let's say, F applied parallel or F applied. I want to work out what that is. I need to consider all the forces in the parallel direction. And therefore I use F applied, Fk, and F parallel. That's why I draw in my components on my rough diagram. You can also call it your rough diagram. You can even scratch it out after your exam if you want. But the point is that you draw it in. Let me show you one like this. Now this is obviously slightly more complicated because the applied force is not parallel to the slope like it was in the last one. It's at an angle. So I'm going to do this quickly. Watch what I'm doing. I'm going to draw the slope in pencil. Slope, 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 like that. Draw the dot in as your object. Weight is going straight down. That's Fg. Normal force is going 90 degrees to the surface. That angle is more or less 90 degrees. Try and make it as close to 90 as you possibly can. Friction, let's assume the box is moving up the slope like that. Friction is moving down the slope like that. So Fk. And now, F applied is not going parallel to the slope. That would be wrong. F applied is going at an angle relative to the slope. So now that I've drawn the slope in, remember the slope is here, I know that F applied must go at an angle relative to the slope. Here is your 15-degree angle. Okay, it's relative to the surface, to the slope. So obviously we don't put the angle in there. We're just going to call this F applied. And again, this is the free body diagram that you draw for me for marks. You get a mark for each force. You do not break the forces up into their components, But when we do our Newton's law question, it is useful to do a rough version where we do break it up into components. And let me just show you what that would look like. If G has a perpendicular component and a parallel component. So this would be FG parallel because it's parallel to the slope. This is FG perpendicular because it's perpendicular to the slope. And because FG is not the only force acting at an angle, F applied is also acting at an angle, it will also have components. This would be F parallel, F applied parallel, and F applied perpendicular. Now, how would I use this in a question or a calculation? If the question asks you to solve for F applied, so say they ask for F applied, you will say, okay, cool. F applied, or let's rather use, let's say the question asks you to solve for friction. Let's use a simpler one. Let's say the question asks you to solve for kinetic friction. You will say, okay, cool. I want kinetic friction, and kinetic friction is parallel to the slope. Very, very important. We've got parallel to the slope, parallel, and we've got perpendicular to the slope. Parallel to the slope and perpendicular to the slope. When I'm looking for friction, friction is a parallel to the slope force. I care about all the forces parallel to the slope. So I will care about friction, I will care about FG parallel, and I will care about F applied parallel. And I will add those three together. So I'll go F net equals MA. The three forces that I care about would be FG parallel, F applied parallel, and the friction. Those will be the three forces that I put together in my formula to help me solve for friction. And students often say, but ma'am, why are we forgetting about the normal force? Well, look at the normal force and look at FG perpendicular. Those are 90 degrees or perpendicular to the slope. So I would put those together in an equation. Those two belong together in an equation. And the parallel ones belong together in an equation because they're acting along the same plane. What about if I have two objects that are connected? Let's talk about this quickly. If I have two objects that are connected, I need two free body diagrams. Two objects connected, two separate free body diagrams, and it'll look as follows. In the first situation, I've got A and B. Now, A, let's do the free body diagram for A. Draw it as a dot. A is on a surface, so it's got the normal force acting up, Fn. It's got Fg acting down. Then, think about this carefully, grade 11s and 12s. If I tell you that the situation is being pulled to the right, so delta x or the displacement is to the right, that means that A is moving to the right. But how is A moving to the right? Only B is being pulled by an applied force. Well, A is moving to the right because of the tension in the rope connecting A and B. So a tension force will pull A to the right. Tension. So if there's a rope or a string connecting objects, there's tension in that rope. I did do a video on this, so I hope you go look at that video. And then assuming that this is a rough surface, or assuming that there's friction, friction will act to the left. Okay? We don't know if this is a Newton's first or second law question. We don't know if these objects have an F net of 0, so the relative lengths of the arrows are not certain. I don't know if I must make T and FK equals what I mean. What about B? Well, draw a nice big dot for me. Extra big for B. I'll show you why now. Okay, please make it look like a dot though. Okay, mine looks more or less like a dot. I've got Fn acting straight up. I've got Fg acting straight down. Just try and make this N a little bit smaller, like F baby N. I've got an applied force pulling B to the right. So that will be F applied. And now, think about B. B is also moving along the surface, so there's also a frictional force acting to the left, Fk. However, this string, the tension in this string is also affecting B. So think about it. B is dragging A along. Okay, someone is pulling B. B is, because it's got a rope connected to A, B is dragging A along. And that tension is pulling B back a little bit. Okay, it's pulling B back a little bit. So the tension for B is actually going to the left. Another way to remember this is the tension goes in opposite directions. So A will experience a tension to the right, B will experience a tension to the left. Those two tension forces are the same, which is why I can label both of them T, because they are the exact same force. Okay, so the tension for A pulls A to the right, the tension for B pulls B slightly to the left, and take a look at why I made this dot so big. Tension is acting to the left, parallel to the slope, but friction is also acting to the left, parallel to the slope. So I made the dot nice and big and fat so that these arrows, tension and friction, are parallel to each other. Let's do one more situation like this. Let's say we've got A is the object on the table and B is the hanging object. Well, A, because it's on a table, it has a normal force acting straight up, Fn. All objects that have a mass have a gravity or force of gravity or weight. Which way is the tension in the rope pulling A? Okay, B will move down this way, let's assume. Let's assume A moves this way. The rope, or the tension in the rope, is pulling A to the right. So tension must go to the right, and then there's friction to the left, Fk. That's for A. Done. Now, what about for B? Now, think about B carefully. B has a mass, therefore it has a weight. The weight acts straight down, Fg. But is B on a surface? Is B on a table? No, B is not on a table. Therefore, there's no normal force for B. No normal force for B. Normal force is when the object is resting on a surface. It's the force that the surface exerts on the object, okay, that it's in contact with. But something is pulling B upwards a little bit. Yep, it's the tension in the rope. So tension is pulling A to the right and it's pulling B up. Now, once again, knowing how to draw free body diagrams is absolutely vital for you. You can even see that in some of these examples, I was kind of showing you how it's going to lead on into Newton's laws, where we have to create these little equations and solve for things. So you need to know how to do this. So I'm glad you watched this video. I hope you watched all the way. Please share it with your friends. Comment what you want to see next, and I hope to see you in future videos. Bye, everybody.